So let me know when I can start.
Okay. Now it is a pleasure for me to present the next talk of this seminar. Then Professor François Delarue, this is the presentation, and the chairman is Professor Anna Dubois. Please start.
Okay, thank you very much. It's a pleasure for me. It's a pleasure to me to present François Delarue. Thank you very much for accepting to give a talk in our seminar. We are happy to see you and to know your work. Let me just say some words about your background, your scientific interests. So François, Professor Delarue, is a full professor of the Université Côte d'Azur in France. His PhD advisor was Professor Pardoux de Marseille in France. He's a specialist in stochastic analysis, included mean field particle system and application to partial differential equations. He is an award holder IMS Dobbs Prize for his research book with René Carmona on mean field games. Actually, nowadays he is a director of ERC project dealing with the mathematical theories, numerical tools for mean field models for statistical state of population. He's the author of many research scientific papers, and he's a highly cited author. So today he will give a talk about selected topics on the mean field control. Please, François, you can start. Thank you very much.
Okay. Thank you, Anna, for the very nice introduction. So this is a great pleasure for me to be with you online. And so indeed, I'm going to speak about one of my subjects, which is called mean field control. I'm going to say what it means. And when I say that this is selected topics, in fact, there will be questions of approximation, and you will see which kind of approximation that I have in mind. I have to say that these are based on two works. The first one is with these two young people, Samuel Dodin, who is in Nice now as a postdoc, and Joe Jackson, who is a postdoc in Chicago. And another work with Mattia Martini, who is postdoc also with me in Nice. So to start with, I'm going to give you a short introduction to this question of mean field models and mean field control, and try to explain to you what we want to do, at least from a mathematical point of view. Very briefly, here, what I would like to study is optimization problem, or let's say control problem, over a very, very large population. But for sure, to do this, I need some further assumption on the model. And those assumptions will be that there will be a kind of symmetry between the players involved in the system, and the interaction that they have is going to be called weak interaction. So I'm going to show you what it means. And basically, I want to optimize or minimize, let's say, a common energy associated with all the players, so all the community, all the population of these players. And this is the same as saying that there is a chief on the top of the players, and the chief tries to say to the players what they have to play so that you minimize some cost associated to the whole population. So this is a kind of cooperative problem. And I have to say, I'm not going to speak about it, but maybe you heard about it. This is not exactly the same as mean field games. In game theory, people are selfish, so they don't care about the state of the population. They care about their own state, and so they do not cooperate. And at the end of the day, what you have a look at is kind of compromises between particles. So this is not the same. Here we are looking at optimizers, which is certainly easier from a mathematical point of view. let me just give you a very small picture to give you a kind of possible application. So you have a flock of drones, and you may guess that you want to optimize their use. Let's think about application to farming, agriculture, for instance, and this could be you could try to optimize the way you can use those drones for your field, for instance. A bit of bibliography. The subject started, let's say, 15 or 20 years ago with these people. So in France, there was Pierre Williams and Jean-Michel Lastry, and there were also people in Canada, those people in Montreal, Wang Kens and Malame. And then the subject started to grow on. Dan Laker in the US, Ariella Briani in Italy, Pierre Cardalaga in France, Yves Ajdou in France, Wilfried Gangbo in the US, and so forth. And from a mathematical point of view, this is very related, and this is what you are going to see, to a control theory on Fokker-Planck equations. And this is exactly what you are going to see next. And recently, you had many efforts on the analysis of the Hamilton-Jacobi equation that you have that is associated with this control theory on Fokker-Planck equations. So one of the difficulties is that then the Hamilton-Jacobi is defined on the space of probability measures. And so you have some works to see how this could be studied. The two questions I have in mind in this talk, the first one is how to pass from a model with a finite number of players to an asymptotic model with an infinite population. This is really the first question I'm going to have a look at in this talk. And the second question I'm going to discuss is how to come back to finite dimension in an efficient manner. So you will see that maybe for numerical purposes, even though there is no numerics in my talk, this is a natural question to try to come back to finite dimension in the end in order to simplify the analysis at some point. Okay, now let me discuss quite briefly about precisely the model I have in mind. So I'm starting with the system with n particles or n players. And even though you know nothing about probability, don't be afraid. This will be very easy. I will switch to PDEs as fast as possible. So here, this is the motion of one player. So I is the index of the player. And again, there are n indices, and all of them are in RD. And they evolve according to some velocity field. So alpha is a velocity. It could be a function of x, so this is a velocity field, or it can be any velocity you want at a given time. And here, this is what we call a Brownian motion, so meaning that there are some local fluctuation around the dynamics driven by the velocity alpha. If you think of the drones, there could be a local variation in the behavior of the drone. And so here, xi is really the position or the state of the particle at time t, and so for player number I. Time is in finite intervals, so it starts here from a given time t0. It could be t0 equal to 0, and the end of time is finite, and this is called capital T. And here, this is the initial state. Okay, and now what I'm going to do is to associate with all these dynamics a cost or an energy. So for those of you who know control theory, the shape of this cost is very standard in control theory. If you know nothing about control theory, then I have to explain a little bit to you what it means. But this is very standard kind of functional that you have. So there are three terms inside this energy. So there is a terminal state. So you see that this is time t here. And so I have a look at the state of the population at terminal time. I have to say exactly what is the definition of this term in red, mnxt. And G of this is a kind of energy or potential energy on the particle system at the terminal time. And there is a cost associated to that. And now between the initial time and the terminal time, I do basically the same. There is an instantaneous potential energy associated with the state of the whole population. And plus, there is a kind of kinetic energy. So L is what we call a Lagrangian in control theory. You can think of this L as being the square of alpha. So this could be, or this would be the square of the velocity. So this would be a kind of kinetic energy, and you make the mean over all the particles in your system. And what you want to do is then you average. So E is for the expectation. So this is a mean over all the possible noises you have here. So all the possible Brownian motions. Once again, I'm going to switch to a PDE formulation, so don't be afraid about that. And then you minimize. So you want to get the best possible velocities. And the best result, this is what we call the value function. So in control theory, the best cost you have is a value function. And so this is a function of the initial time, t0, and the initial configuration, which is a very big vector in which you have all the possible initial states, x01, x0n of your particle system. Okay, and I am interested in the large n behavior of this quantity. This is one of the main results I'm going to discuss in this talk. So let me just explain a little bit the notations. So this M and X, this is in probability theory, what we call the empirical measure that is associated with the system. So if you have all your states, you put a delta mass at any of the states of the system, and you make the mean of that. And this is a probability measure that describes the state of your system. Okay, so this is for this quantity in red. And as a typical instance of this potential energy F and G, you have this kind of this is one example. So you take an interaction energy between two states, X and Y, and then you make the mean with X integrated with respect to the measure M, and the same for Y integrated with respect to the measure M. So this is something that is very standard, that this is an example of an interaction energy associated with the population encoded through a probability measure M. Here, the probability measure, this is a finite measure, or even more, a uniform measure on the tuple x1, xn. So you see that there are plenty of symmetries in this problem somehow, and you would like to see what happens when capital N is large. Okay. Again, there is a PDE formulation of this problem that I'm going to speak about next, meaning that there is a Hamilton-Jacobi-Bellman equation for the value function. So if you know PDE theory, you could think of Vn as a solution to a nonlinear equation in dimension d times n. So the state space is really big. And again, we want to pass to the limit on this. So my question here is about the convergence when n is large, and specifically the rate of convergence. This is one question, one natural question in the field. And I give you some bibliography. First results about this without any rate by using compactness. You have a very nice paper from a probabilistic point of view by Dan Laker a few years ago. With Cardaliaguet, Lasry, and Lyons, we provided, or we gave another analysis, and we obtained 1 over n as a rate in the case when the coefficients are smooth and convex in the measure, and convex as well here in alpha. But the convexity of the measure was absolutely necessary in this work. You can expect that since this is a minimization problem, this is easier if you have convexity. And the next question is what happens if you remove convexity? Basically, this is a natural question from a mathematical point of view. And then you have a more recent paper by Cardaliaguet, Dodin, Jackson, and Takis Souganidis a few years ago, when they claim that, well, if this is regular but not convex, then you have an algebraic rate of convergence, beta to the d. But the beta they had is basically 1 over d to the square. And one question is whether this d to the square is the right exponent, or whether you can do better. And this is what I'm going to discuss in the first part of my results. Okay, first question: what should be the mean field limit? So by mean field limit, we mean that we take n tends to infinity, and what should be the limit of Vn as n tends to infinity. And the guess, I'm not able to prove that at this stage of the talk, but I will give you some arguments next. The guess is that in the limit, you still have a control problem. But the population is somehow infinite, which means that instead of considering a finite cloud of particles, you have a look at a continuum of particles, or you have a look at directly elements of the space of probability. So instead of having those empirical measures, now we have probability measures, and they evolve according to Fokker-Planck equations. So here it describes the evolution of the law of one particle that is submitted to some velocity field alpha and a Brownian motion. So the Laplace here is accounting for a Brownian motion from a probabilistic point of view. And so the control is the velocity field in your Fokker-Planck equation, and you want to minimize this cost. Okay, somehow this is connected, for those of you who know these kind of things, to Benamou-Brenier formulation in optimal transportation theory, except for the fact that optimal transportation is very, very singular. So I'm not going to speak about this, but the spirit is not completely disconnected. Okay, so this is the limiting system. There is a probabilistic interpretation if you know a bit of probability. So you replace the velocity field alpha by some random velocity, which is exactly this alpha t. And then instead of having empty here, solution to the Fokker-Planck equation, then you have the law of your particle. This is exactly the same. The two problems are exactly the same. But I'm not going to speak about the second formulation since this is a seminar in PD. Okay, first thing I would like to do is to speak about this mean field limit and to explain to you, at least for those of you who know nothing about that, what happens when there is no control. So here the difficulty is that I am controlling the dynamics. What happens when there is no control? So let's say that I have a particle system exactly as the same as before, but the velocity is given. This is not the result of some optimization. This is given. And it depends on my own state, and it depends on the global state of the population, this empirical measure. What happens when n tends to infinity? If the field B is not too bad in the limits, the empirical measure converges to the solution of this nonlinear Fokker-Planck equation, which is very much the same as before, except that now B is fixed. And plus we have the rate of convergence. This is something that we know. So we can measure the distance between these sorry about this. Sorry about this. Let me come back to my, okay, sorry, can you see my slides? This empirical measure, so the distance between the empirical measure and the theoretical, or the solution to the Fokker-Planck equation, this is evaluated with respect to some distance on the space of probability measures. So you have first to say what is the topology or what is the metric on your space of probability measures. And again, this is connected to what people are doing in optimal transportation. You are using a Kantorovich distance, or the Kantorovich distance, the definition of which is as follows. So you take two probability measures, mu and nu, you make the difference, mu minus nu, and for sure the difference is a measure, so it is acting by duality on continuous functions. And so here what you say is that you take the supremum over one Lipschitz function. So I'm cheating a little bit because somehow it requires mu and nu to have a first order moment. This is implicit in my definition. And so this is called the Kantorovich-Rubinstein distance, or the one Wasserstein distance. This is so the duality with respect to one Lipschitz function. And the rate of approximation in this or convergence in these two problems then is known. This is something that we can compute. I forgot to say that here in this particle system, typically the initial condition is an IID collection. So meaning that the initial conditions, they are random, and they are independent, and all of them, they have the same distribution as the solution to the Fokker-Planck equation. And then, so the rate of convergence is depending on the dimension. So you see that typically this is n minus 1 over d, where d is the dimension of the space. And so you see that for this topology, this is more and more difficult to fill the space of probability measures when the dimension increases. This is what you are saying. Okay, so this is one result, and then you could compare this 1 over d, so this exponent, to the one I told you about, which is 1 over d squared, the one obtained by these people in this work 2 years ago. And the guess is that we should see 1 over d in this problem as well. This should be very much connected to the one I have I want on this slide. Another result in probability theory is that when you have a convergence, you are wondering about a central limit theorem. So you have the fact that a sequence of random variable, here there are probability measures, converges to someone that is deterministic, and you would like to see some Gaussian fluctuation. And there are some results in this direction that say that, okay, we can retrieve some Gaussian fluctuation of size 1 over the root of n, but then we have to change completely the topology, meaning that instead of working with duality or biduality with one Lipschitz function, we need to work in duality with higher with functions of higher regularity. So instead of working in the space of probability measures, somehow we work in a very negative Sobolev space. So we test with respect to functions which are much regular than one Lipschitz function. So this is a way to speed up the convergence, which is to test with respect to functions which are smoother or which are more regular. So this is something that you are going to observe in my results. Okay, let me come back to the formulation of the control problem. So I have these two costs, f and g, and they are defined on the space of probability measures. And to simplify, because the analysis is not easy, I'm going to assume that there is no boundary, meaning that there is no boundary, and this is compact. So I'm working on the torus TD. So you could guess about what happens when there is a boundary. This would be certainly more technical, and the difficulty in my talk is not here. So the analysis is on the torus. Once you have this, you say you define something that is quite standard in control theory, which is the Hamiltonian. So basically, this is just the Legendre or the Fenchel transformation of your Lagrangian. So this is something that is completely standard. And you make the assumption on the Hamiltonian. Usually, this is the way it works. And I'm going to have two sets of assumptions. The first one, which is what I'm going to call general. So you require the Hamiltonian to be quite smooth, so C2, and specifically to be uniformly strictly convex in the dual variable and the momentum P. So here, this is P is the momentum, and you see that the second order derivatives, they are uniformly lower bounded. And for the cost coefficients F and G, well, you require something that is mild, meaning that this is Lipschitz in D1, okay? I'm not going to use that much these properties. This is just to give you some intuition about the two regimes that I'm going to distinguish next. And plus, I need another assumption, which is that F and G, they are semi-concave. So semi-concave on the space of measures means that you make a linear convex combination of two probability measures. Here you have the convex combination of the images. And there is a loss, and the loss is controlled by the distance between the two measures. And here the distance is exactly this one Wasserstein distance I mentioned before. So this is something that we call general. This is the weaker setting. And another setting is what I'm going to call smooth setting. I'm going to say that there is an index of regularity, S, which is greater than d over 2. This d over 2 is connected with Sobolev embedding, which plays a key role in the rest of my talk. And now the Hamiltonian is very smooth depending on the dimension. This is this CS. And plus the coefficients F and G, they are also semi-concave, but now instead of measuring distances with respect to this topology D1, I'm measuring the distances with respect to minus S. So the norm in the higher negative Sobolev space. So this is more demanding, more difficult to be semi-concave in this sense. And there is another constraint, which is that I require the derivative of f and g. I'm going to tell you what those derivatives are, df or delta f over delta m and the same for g, to be regular in this variable depending on s. So this is the CS norm. So what is the derivative of a function defined on the space of probability measures? So this is an extension of the derivative on the space of measures. So you take two probability measures, m1 and m2, and you want, for a function of phi that could be f or g, you want to expand the difference. And so you see that you do a kind of Taylor expansion at the first order, and you say that the difference of the two measures acts onto a gradient. And so this gradient is computed along the convex combination of the two functions. And the gradient is a function because by duality, the gradient should be a function acting on the difference of the two measures. So this derivative delta f over delta m, this is exactly the same object as the one you have here. I know this is a bit technical, but this is to tell you that I need regularity in this variable dot or this variable y in the definition of my gradient. And the level of regularity is dictated by the dimension. This is exactly what it means. Okay, now these are my results. I take the difference between the two value functions. So here, this is the one that is associated with the particle system, computed at a vector of initial conditions, so in dimension d times n. And I compute the limiting value function, the limiting object when n is equal to infinity. I compute it. Normally, this is computed at a probability measure. And here, the probability measure that I take, this m and x, this is exactly the uniform measure on the vector x. And so I have an upper bound and a lower bound. The upper bound in the general setting, so the weaker one, this is to tell you that I recover exactly the same thing as for the results when there is no control. So this is completely consistent with what happens when there is no control. The lower bound is more difficult. And the best we have is that instead of having 1 over d or minus 1 over d, we get, let's say, 2 over 3d. So this is, we guess that this is not optimal, but this is not that far from what we expect to be optimal. That would be this 1 over d. And in the smooth setting, when this is, we have this CS regularity. So this is equivalent to the central limit theorem in the first particle system I mentioned. We get C over n as a bound, which is really good, and C over the root of n as a lower bound. So this is consistent somehow with the central limit theorem. And when the coefficients are convex, in fact, this guy is 0, and we recover the older result I got with Cardaliage, Lasry, and Munch. Okay, so these are the results in this setting. Okay, so now you could say how to prove this, and maybe this is what I'm going to say now. So a few words about the strategy of proof. The strategy of proof, this is purely PDEs. So I'm coming back to the equation for the value function. This is what I told you before. If you don't like control theory, you can think of this problem as an approximation problem for a very big Hamilton-Jacobi equation. So you see that this is an equation in dimensions d times n, and the dimension of the space is larger and larger, and you want to pass to the limit when n tends to infinity. So it describes the best possible cost when you let the initial time and initial point vary. Just one remark for those of you who are wondering, once you have the value function, you get the optimal feedback function or the optimal velocity field that you have to play. And this is exactly given by the derivative of the Hamiltonian computed at the derivative of the value function. So here, this is xi, so this is the optimal velocity for player number I. Okay, so this is a side remark if you are wondering what is the connection. What is the strategy of proof? The strategy of proof is to take the limiting value function u computed at m and x. So x is a vector in dimensions d times n. And we want to see this u of m and x as an early solution of this equation. So we want to compute all the terms in the left-hand side when I am replacing Vn by u of that. and prove that this is not exactly 0, but this is something that is really small. And if I know that this is very, very small, basically I'm done and I get the rate of convergence. Okay, one very difficult technical thing in the field is to write down the equation for U. So U is an object in infinite dimension defined on the space of probability measures. And there should be an equation for that that would be the Hamilton-Jacobi equation, but in infinite dimension. And so this is this equation. So I don't care that much about the exact shape of this equation. The only thing I'm saying is that this is the analog, but in infinite dimension, when n is equal to infinite, this is the analog of this top equation. And you have exactly the same derivatives as before, this delta U over delta M that appears in this equation. And the very good point is that there is a nice dictionary to pass from those derivatives, delta U over delta M, to the standard derivatives. So in particular, if I take this Laplace term, so the Laplace in the direction xi, I can compute the same term, but when now I replace V by U. And I know how to compute this in terms of those derivatives, delta U over delta M. So this is part of the theory. And then what you have is that you recognize exactly that when I compute this term, at the first order, I get exactly this one, which is exactly corresponding to the one I have in the Hamilton-Jacobi equation for you, plus a remainder that is in 1 over n squared, n times second order derivatives. And the fact that I have second order derivatives might be a problem, because if U is not smooth, I don't have those second order derivatives. But assume for a while that I have those second order derivatives. Then I have n of these derivatives, or n of this Laplace. So I have n divided by n squared, and this is the way I get this 1 over n in the very smooth and convex setting. So this was this older result I mentioned you, so with Cardaliaghe, Lasry, and Young. So just a summary of where we are. If this U, the solution to the limiting Hamilton-Jacobi equation, is very smooth, then this is fine, we get 1 over n. And in fact, we don't have so many cases when this is true, and we know that this is the case, so there is a classical solution to this limiting equation when I have smooth coefficients and convex coefficients f and g. Now, what happens when I remove convexity? And our strategy of proof is to say, okay, in that setting, the value function U might not be smooth. I may not have a classical solution to the Hamilton-Jacobi equation. There might be some singularities. And so we are going to modify. What I want to say is that this is exactly the same as what you have in vanishing viscosity problems. In vanishing viscosity problems, so let's say that you have Hamilton-Jacobi equations plus a small noise or a small Laplace, you wonder about what happens when the viscosity tends to 0. Here, the viscosity comes from the fact that all the players have a noise. But when I have many, many players, somehow there is an averaging phenomenon, and the noise that is, the common noise that is in the system is of a smaller and smaller intensity when n tends to infinity. And so this is a kind of vanishing viscosity. And so now you could say, let us try to apply the same tools in infinite dimension as the one we have in finite dimension for Hamilton-Jacobi equations with a small viscosity. And so this is the principle of this proof when I don't have a convexity, when I don't have a classical solution to Hamilton-Jacobi. So we modify U. And so this is the second main idea in my talk. The first one was using the Hamilton-Jacobi equation in infinite dimension, and the second one is modifying this equation. And the difficulty is how to modify in infinite dimension. And maybe this is something that you know. There are some ways to do that, and this is, for instance, subconvolution. I'm going to give you the definition of that. Subconvolution, this is an object that is very, very easy to use when I am working in the Hilbert space. Okay, I'm going to give you the definition next. And so the difficulty here is that I'm not working in a Hilbert space. I'm working on the space of probability measures. And so then you remember what you have to remember what I said for the central limit theorem. For the central limit theorem, I told you somehow we embed the space of probability measures in a very negative Sobolev space. And here I'm going to do the same. I'm going to say my probability measures, I'm going to see them as an element on H minus S, so the usual Sobolev space of index minus S on the torus. So the Fourier expansion of the norm minus S, if you want to be clear, this is exactly this one. So this is the Fourier expansion of the norm. So this is the usual W2 minus S space on the torus. And now I do my sup modification. So I take the limiting value function, and this is what we call the sup modification of it. So the way it works is that you take a distribution in H minus S, so this is Q, and you compute the supremum between U of Tm, so M is an arbitrary point in the space of probability measures, and then the distance between Q and M squared in the space, in the Hilbert space. And this is penalized by 1 over epsilon. So when epsilon is small, somehow you force Q and M to be very, very close. This is what happens. Okay, now the nice point of this construction is that, so this is something that is very well documented in an article by Lyons and Lasserie. And the very nice point is that we have that U is Lipschitz in our setting, U is concave, and U epsilon by sup convolution, it becomes semi-convex. And so the constant of semi-convexity and semi-concavity is bounded by 1 over epsilon. So you get something that is C11, if you want. So C11, this is not that far from being C2. This is not exactly the same. But if you think of my computation with the second order derivatives, I'm not that far. And the fact that I have a clear bound for the C11 norm is very useful. And this is C11 on H minus S, so on this space, auxiliary space that I am using. So now let me show you how it works. The philosophy is as follows. I have my original value function. I have the modification of it, and the modification by subconvolution is almost a subsolution of the Hamilton-Jacobi equation. So this is something that is very well known in a classical viscosity solution for a Hamilton-Jacobi equation in finite dimension. And here we are doing the same in infinite dimension. So we compute exactly the same equation as before. So this was my Hamilton-Jacobi equation, but for U epsilon. And you see that this is lower bounded by minus C epsilon. So I really see the parameter for the modification. How to apply this, and this will be the end of my sketch of proof. The point is that by duality, the derivative now should be an element of HS, because now I see the probability measures as an element of H minus S. So now by duality, this derivative should be in the dual of H minus S, so that is HS. But since I have Sobolev embeddings and S is really large, and this is where you see the Sobolev embedding, HS is embedded in C2. And it means that, in fact, those quantities, they are nice functions. And so somehow I have a classical solution to this equation here. And so this bound is really meaningful everywhere on the space. And now I redo the same computation as before. Instead of expanding U along the empirical measure, I expand U epsilon, so the modification of it, along the particle system or along the empirical measure. And I pay for two things. I pay for this minus C epsilon. And now, if you remember my proof, so I just have to come back just for a while. I had the second order derivatives before, divided by 1 over n squared, multiplied by n. So this is 1 over n times the order of the second order derivatives. And now this is 1 over epsilon. So when epsilon is small, this is very large. And so I have exactly this term, this residual, and I just have to optimize. And for sure, to optimize, I choose epsilon is equal to 1 over the root of n. And this is the way you get the lower bound in the smooth setting. So when everything is smooth, I have this CS regularity. This is the way, sorry for this. this is the way you get this, this 1 over the root of n. If you remember, I had two results, one in the smooth case, non-convex but smooth, and one in the non-smooth and non-convex. So I'm not going to discuss the non-smooth regime. Then there is another modification, and then you have to pay more for this additional modification. This is the price you have to pay to pass from a D1 to H minus S. So this is the reason why there is a loss. And in the end, this is the way you got this this exponent beta D that is 2 over 3D that I mentioned before. So the conclusion of this computation is that we are using the limiting Hamilton-Jacobi. We expand it. If this is smooth, this is okay. If this is not smooth, well, then there is an issue, and we modify and we see how much we lose. Once you have the difference for the value functions, you may think about the difference for the optimal trajectories, which is a more difficult question. I'm not going to give you the results precisely. In the work I mentioned before with Cardalaguet, Lasry, and Lyon, so the one in the convex regime, we know exactly what is the distance between the optimal trajectories and the optimal feedback functions. We know how to quantify that. When this is non-convex, even though this is smooth, you have to be very careful, because you have some singularities in your Hamilton-Jacobi equations. But the very good point is that they are not so frequent, and you can prove that you have some part of the space without singularities, and then you can quantify on those parts of the space the distance between the optimal trajectories. So this is a bit technical, and I prefer not to discuss about this. So this is the end for my the results about the approximation. I know that my time is over. I just want to say something about the other part. So I won't be able to say more about this, but a lot about this, but just to tell you something. Here, I mentioned to you that I was starting from a model with n players, and I told you there is a kind of scalability property, meaning that somehow this is the same in terms of value function, but also of optimal trajectories or optimal velocity. This is the same if n is equal to 10 to the 4 or n is equal to 10 to the 10, and I can directly solve the model with n is equal to infinity, and I get something that is meaningful for these two scenarios, for these two cases. But this is not suitable to this. I mean, now the question is how to solve the limiting problem numerically or practically. And since this is a problem in infinite dimension, this is an issue. And what I wanted to tell you is that you can come back to finite dimension without using particles, but by doing some kind of Fourier Galerkin approximation. So when you have your Fourier measures, what you do is that you expand in Fourier your measures. We are on the torus. You expand your measures in Fourier, and then you truncate the Fourier expansion. And in this manner, if everything is smooth and convex, you get rid of approximation, which are much better than the one you have from the particle system to the limiting mean field equation. And so what I wanted to tell you is that I started from finite dimension, then I jumped to infinite dimension, and then I wanted to come back to finite dimension by using this Fourier Galerkin approximation of the solution to the mean field equation. I'm not going to go further, but the philosophy is that if you do so, you can approximate the limiting problem by something that is in fact more efficient. So the price is lower for the same rates of approximation. So let me stop here, and I thank you for your attention. Thank you.
Okay, François, thank you very much for this very nice talk. Let's ask the audience if there are some questions. If there's some questions from the audience. So someone has some question to ask to Professor Delarue. Please, you can use yes, you can use chat or also your microphone. While people thinking, I just I have some short question or not a big question. What about the numerical approximation? You told at the beginning that you want to talk about it, but I'm sure that you have some results about numerical approximation.
No, myself, no. So some people are doing numerical approximation. So what I wanted to tell you here is that I have in mind, or this is part of the results that I wanted to present. So this was these two last slides to tell you that using Fourier-Galerkin expansion, you get something that is a possible nice discretization of the limiting Hamilton-Jacobi equation. And this is something that we want to do now. So we have the rate of convergence, and now we want to test this from a numerical point of view. So it means that, to make it clear, it means that in my control problem, I am replacing the measure mu you have in the Fokker-Planck equation by the truncation. So dn is the Dirichlet kernel, and so mu convoluted with dn is the truncation of the measure, and I do the same in the cost. And this is a way to parameterize your control problem with a finite number of parameters. And now this is a way to reduce the Hamilton-Jacobi equation to the limiting one to a space of finite dimensions. And the accuracy is quite good, meaning that these are our results, that if the coefficients are higher regular, so S is the regularity of the coefficients, then we can get a rate of convergence, let's say, for the value function, but this would be more or less the same for the optimal velocity, that decays like 1 over n to the s, where n is the number of Fourier coefficients that are needed. So this is just a discretization result I wanted to speak about, but now this is something we want to put indeed in, or we want to turn to the numerics, but I have no numerical example to show to you. Now, what I can say about numerics is that, let's say that the main expert is Yves Ajdou. So if you're interested in that, there are very nice reviews by Yves about numerics. There are several strategies. You could think of trying to approximate directly the Hamilton-Jacobi equation, but in fact, this is difficult because this is an infinite dimension. So what people are doing instead is that they write down the Pontryagin system. So this is a control problem. So in control problem, in control theory, you have the Pontryagin principle. This is a kind of first order condition. And this is a way to characterize the optimizers by a system of two PDEs, one that is forward and one that is backward. And then here, these are two PDEs in finite dimension, and people are working on this system of two PDEs to solve numerically the problem. This is one of the main approach. So I'm sorry, I have no simulation no numerical example to show you. But again, you can have a look at the work by Yves, and I'm insisting on the fact that directly solving this big equation in infinite dimensions, certainly this is challenging from a numerical point of view. And so people are doing this, working mostly on this Pontryagin system that you get.
Yeah, for optimization system. So thank you very much. It was just a curiosity. Are there any other questions from the audience? Please. Okay, if not, we thank you again.
Thank you. Thank you.
Thank you very much. And
I'm happy to answer questions by mail or any questions about bibliography. So I guess you have my email. So do not hesitate.
Yes. Okay. Thank you very much. Thank you very much. So
thank you.
Okay, thank you very much, Professor François Delarue, and thank you very much, Anna Dubova, for the introduction. And